Hey, I'm Auryn from Gnosis Guild. I'm going to talk today about collaborative confidential compute. So this is a class of problems that we're building some solutions for. There's a variety of protocols and organizations and whatnot building solutions around this or kind of ideating on it, and a bunch of really interesting research that has happened over the last few years pushing this space forward. But yeah, going to kind of introduce the concept and then a new trilemma, just because what's a blockchain protocol without a new trilemma? So aggregating inputs from multiple parties is this kind of fundamentally powerful technique. It's a critical component behind a lot of our most interesting, most impactful, the most interesting and impactful things that we do, right? It's a critical component to our democracies, to our markets, to training AI, to doing research, and to producing social media feeds. I'm likening it to the spirit bomb here for any Dragon Ball Z fans. You can, I guess, many small inputs from many people can produce things that are dramatically more impactful than any individual acting alone. But a lot of these kind of systems come with this fundamental trade-off, this big caveat in that privacy in them sucks. If you're aggregating inputs from many people, generally it means making a huge compromise on privacy. And where these systems do have some element of privacy baked in, then they tend to come with some other set of caveats that make them equally untenable. Part of this is due to economic influences, right? There's this firms have this massive economic interest in, this financial incentive to hoover up user data as much as possible, to silo it, because the information asymmetry is the thing that's valuable. But beyond that, there's this deeper kind of structural challenge that I'll describe here as the collaborative computing trilemma. In an ideal world, you can take multiple inputs from many different parties, arbitrarily aggregate them in a way that preserves privacy for people providing inputs. But in practice, we end up compromising on at least one of those properties: aggregation, verifiability, and confidentiality. And this is a forced compromise, right? Things are fundamentally incompatible in a way that forces us to always make a compromise on one of the properties. And so just to be clear on terms, by verifiability, I mean that participants and observers can independently check the integrity of a system and verify the correctness of its outputs. By confidential, I mean that inputs and intermediate states remain private, and only the kind of pre-agreed on aggregation is revealed. And then lastly, that the system can meaningfully aggregate. And what I mean by that is can meaningfully manipulate, combine, and compute over data from multiple independent sources without having to, ideally, without having to collect all of that data in one central place, give one party access to that data. The collaborative compute trilemma essentially states that we can pick any two of these three and then must compromise on the third. So a few familiar examples just to kind of ground this idea. Each compromises on at least one of these properties in order to achieve the other one or two. So we'll start with some systems that are reasonably familiar probably to a lot of folks here. First is programmable blockchains like Ethereum. So we have this shared state machine and some consensus rules that allow a network of nodes, a network of validators, and kind of external observers to follow the network or participate in producing blocks for the network to validate that inputs to the network, that the state transitions on the network all follow the set of rules for that network, right? That the state transitions are valid, that the audit they are applied makes sense, or at least there's a universal agreed on order of the application. And in other words, to take many inputs and aggregate them in a verifiable way. But the trade-off here is that in order to do this, anyone needs to be able to look at the historic inputs to recompute the current state. So it's an explicit trade-off of privacy in order to achieve verifiable aggregation. A more kind of practical or traditional example would be something like a English auction, a first price auction, right? So this is your prototypical auction where bidders raise their hand or shout out their bid, raise a paddle, something like this to signal that they want to place a bid in the auction. There is agreed upon rules on how bidding works, like every bid has a given increment over the current price, or the bidder can shout out an arbitrary increment. But being able to observe the inputs, the bids, and knowing in advance the rules of an English auction, any participant, any observer can guarantee or can be kind of ensured of the correctness of the outcome. So again, it's verifiable and an aggregation, but at the cost of privacy. An alternate auction type, which is generally considered to be a bit more economically efficient, is a sealed bid second price auction, a victory auction. And so in practice, the way that this works in most cases is you have an auctioneer who is trusted to accept all of the private bids, to calculate the result, the bidder and the price that they pay, and then to reveal only that information to the public in order to settle the auction. And so in this case, you're trading off both confidentiality in that you're still having to reveal your information to the auctioneer, as well as verifiability in order to have this aggregation of bids that is more privacy preserving, but still not kind of perfectly privacy preserving. Again, a compromise on verifiability and confidentiality in order to achieve this specific aggregation. So another approach to this, or another kind of branch of these trade-offs here, is where we choose to constrain what types of aggregations or a capacity for aggregations in order to have something that is verifiable and confidential. And so this is where Zcash, privacy pools, Railgun, these kind of private UTXO-based systems fit in. You're explicitly trading off your ability to do aggregations, to have kind of shared secret state, in order to have a system that is both private or confidential and verifiable. So these systems hide your inputs and allow you to benefit from the privacy set, but there's no shared secret state that participants can collectively manipulate. There's no aggregation. And then I think the most typical trade-off in this space here is confidential aggregation without verifiability. The prototypical example here is secret ballot voting. The state of the art in most worthwhile democracies is to step into a voting booth, write your vote on a piece of paper, drop it into a box, and shake the box with all of the other ballots. And this gives you a confidential aggregation, but at the explicit trade-off of verifiability, right? You are probably not present for the counting of the votes. There's no way for you to kind of mathematically verify that the vote corresponds to the inputs. But yeah, this is an explicit trade-off so as to give this confidential aggregation to enable things like coercion resistance, collusion resistance. So what we're working on at Enclave is a solution to this confidential compute trilemma. The idea is to allow many private inputs to be computed collaboratively, or computed over collaboratively, producing a verifiable output while preserving privacy for inputs in intermediate states, and then giving you a verifiable outcome with game theoretic guarantees around the input and intermediate state privacy. So in other words, aggregation, verifiability, and confidentiality packaged together in one product. And I want to be clear here that this is not without trade-offs. The trilemma still applies, but we do think that it's a best-in-class solution to this category of problems, essentially allowing us to radically distribute trust in privacy and guarantee it with game theory and economic guarantees in a way that has not been done yet. We are able to have cryptographic guarantees of correct execution with game theory guarantees of secured confidentiality. So what ultimately enabled us to build Enclave is this convergence of essentially the holy trinity of cryptographic methods maturing simultaneously over the last few years. So we have zero-knowledge proofs, fully homomorphic encryption, and multi-party computation. ZKPs allow us to make the entire process end-to-end verifiable. Fully homomorphic encryption allows us to compute over encrypted data such that we can produce an output ciphertext that, when decrypted, gives us the same result as if we ran the computation on plain text. And then MPC allows us to radically distribute trust in the keys that can ultimately decrypt the output ciphertext and could, in theory, decrypt any of the inputs as well. And this is where this critical fourth component comes in there, a system of economic guarantees. So penalties and rewards for malicious and honest behavior, respectively. So we get, again, cryptographic guarantees of correctness with game theory guarantees around privacy. And this is where you folks come in. So we're gearing up to launch Enclave in Q1 next year. And we need a critical mass of cypherpunks to run what we're calling Ciphernodes in Enclave. What's ultimately going to make Enclave interesting, what's going to make it useful, what's going to make it valuable is having a very large, very broadly distributed, very high quality set of node operators collectively securing the collaborative confidential compute requests on our network. And so we're running an internal testnet right now and are going to start opening it up to external node operators here in the near future, the next few weeks or month-ish. And so, yeah, we're just starting to kind of collect interest from potential node operators. So, yeah, I guess if you're interested out of curiosity, out of cypherpunk instincts, for fun or for profit, then yeah, head over to enclave.gg/Ciphernode. And yeah, we would love to hear from you, or just come find me after the talk. We have a little booth in the back. Yeah, we're really excited for what we're enabling with Enclave. And again, critical component is hitting that critical mass of great quality node operators. And I think the folks here showing up for Cypherpunk Congress is that core for us. We really want to make sure that the folks getting involved early on are aligned and in it for the ethos for the cypherpunk ethos. Yeah, so that's it for me. Thanks, everyone.